Okay, so if you read the sheet on electrostatics like I asked you to, you would have already heard most of this. Elementary charges are protons and electrons. We call them elementary charges because back when they were discovered, we were thinking that there would be no possible way to have a charge smaller than that. You'll often see something written as 1e. Now you might think the E means electron, but it really means elementary charge. Now, we know that we can actually have charges smaller than an elementary charge now, but we didn't back then, so we still call them elementary charges. So you'll often see 1e equal to plus or minus 1.602 times 10 to the minus 19. Plus if it's a proton, minus if it's an electron. So we can say the charge on a proton and an electron is 1e or negative 1e in terms of elementary charges. But if we're talking in terms of the metric system, then in metric, the measure of charge is a coulomb. And it's spelled C-O-U-L-O-M-B, a coulomb. Okay? So one electron is a negative 1.602 times 10 to the negative 19 coulombs, and one proton is positive. If I assume you all know the structure of an atom, so we have our protons and our neutrons in the nucleus, and our electrons around the outside of the nucleus. If an object is negatively charged, then it means it's gained electrons. We all know that. But sometimes people will tend to think that if an object is positively charged, that it must have gained protons. There's going to be no movement of protons as an object gains or loses positive and negative charge because the protons are stuck inside the nucleus. The only way you get them out is in a nuclear reaction, and you'll know if that one happens. But it's really easy to gain and lose electrons. I can do it by just rubbing my hand together. I can take electrons off my fingers, or I can rub them on the floor or the paper or my pants, and I can exchange electrons. So if an object is negatively charged, it means it's gained electrons. And then if an object is positively charged, it's lost electrons, never protons. Okay? Now, I also assume you know that positives and negatives attract, and two positives repel and two negatives repel. So that goes back to when you were little kids and learning about electrostatics. They probably just didn't call it that then. I think you probably also know what happens if I have one object that has, let's say, a positive 4 elementary charge, and an object that has like a negative 2 elementary charge. If I have these two and I bring them together and I touch them, so whenever we have two oppositely charged objects and they touch, I assume you probably know what happens. But just in case you don't, then if we were in class, I would say, tell me what happens. But what happens is there'll be an exchange of electrons, because this guy, the negative 2 guy, has 2 excess electrons, and the positive 4 is missing 4 electrons. He's 4 short. So if you were to listen to the conversation, the positive 4 guy would be saying, I'm short 4 electrons. This is so unfair because you have 2 extra, and if you were nice, you would share them with me. And so the positive's going to whine and whine until finally the negative 2 guy gives 1 electron. And so the positive 4 now becomes positive 3. It's only short 3 electrons. And the negative 2 one, it now only has 1 extra electron. So it's now negative 1. And so the negative 2 guy would say, happy now? And the positive 3 one would be like, no, because I'm still short 3 and you still have 1 extra, so it's still not fair. And so finally the negative 1 guy would share another, and so this would become positive 2, and this would become neutral. Now you might think that all would be done because now this one's neutral. But it isn't, because this one's like, but I'm still short 2 and you're not short any. It's still not fair. And the positive 1 will continue to whine until finally they end up with the same charge, both at positive 1. So whenever you have two opposite or two differently charged atoms or substances, and they're brought together and touched, there'll be an exchange of electrons until they end up with a balanced charge. They don't even have to be positive and negative. One might be positive 6 and the other might be positive 4. And it would still happen because one still has more electrons than the other. So they'll share until they balance out. One way to figure out what the final charge would be is just keep moving one electron over at a time until they balance out. The other option is add them together and divide by 2. When it's positive 4 and positive 6, just move one over and it'll be okay. But if I give you like negative 20 and positive 40, you might be not loving me by the end. So add them together and divide by 2. So plus 4 minus 2 is about plus 2. Divide by 2 is plus 1. And lo and behold, that's where they end up. Okay? So that's if two objects that have different charges are brought together and touched. We already said that like charges like charges repel, opposite charges attract. That's going to lead us to an equation. Now, the wonderful thing about electrostatics is that it mirrors gravity. So if you remember, the gravitational force of attraction was, you better remember, you just wrote the test, G m1 m2 over r squared. So in electrostatics, in gravity, this says that the gravitational force between the two objects is dependent upon the mass of the two objects and the distance that the two objects are from each other squared. In charge, the letter for charge is Q. So the charge on one electron is negative 1.602 times 10 to the negative 19 coulombs. So that's the Q of an electron, the charge of an electron. Okay? So obviously the electrostatic force between two charged objects is going to be dependent upon their charge. And it should be dependent upon the distance they are from each other. And so our equation becomes FQ, where Q is the subscript, meaning it's for charge, is equal to K Q1 Q2 over R squared. It looks identical in form to the FG equation. Q1 and Q2 are the charges of the two objects. R is the distance between them, center of one to the center of the other, and K is called the electrostatic constant. And it's a nice, easy constant to remember. Whoops, off the page, but it is, I swear. It is 9 times 10 to the 9th. Newton meters squared, just like this guy was Newton meters squared, but this time it's over coulomb squared as opposed to kilogram squared because they're charge instead of mass. Science 12-2 people, you would know it as 8.988 times 10 to the 9th, but in physics we always just round, in high school physics, we round to 9 times 10 to the 9th. Okay, so your homework for class tomorrow that you're not going to have, is using this equation to figure out the electrostatic force between two objects. Obviously, when we put 9 times 10 to the 9th in here, multiply it by 2 coulombs and divide by meters squared, we'll be left with just newtons, which is what force is measured in. The only thing that's a little different is whether it's an electrostatic force of attraction or repulsion. For gravity, it was always attraction. But for charge, it doesn't necessarily always attract. Sometimes it might repel. It depends upon the nature of the charge. When we talk about the nature of the charge, it's kind of like when we talk about your nature. Some days your nature is pleasant or positive. Other days you're a little snarly or negative. So when we say the nature of the charge, we mean is it positive or negative? So if two charges have the same nature, both positive or both negative, then the FQ is going to be positive. And if the FQ is positive and the two charges are positive or the two charges are negative, they're going to be repelling. So a positive FQ means it's a repelling force. If one Q is positive and one is negative, it's going to give this overall value a negative. So if FQ is a negative, it means it's an attractive force. right?